Continuing from the last video, this is an example of the swinging room, right? So you see a toddler placed in this room, and notice that the floor, which is the the gray patch here, is stationary, but the room itself is actually moving back and forth. Um, and of course, as the wall is approaching you, your flow looks like this. And then as the wall is backing away from you, the flow goes the other direction. And sure enough, these toddlers, as they're in this room watching this flow come and go at them, adjust their sway so much so that a lot of times they fall over. Um, Now let's look at some physiological markers, some physiological evidence for our ability to navigate through the environment. So we've actually been able to identify neurons in the medial superior temporal area of monkeys that respond to flow patterns. So for example, an experiment done by Britton and Van Wiesel, monkeys we monitored the activity of neurons in the MST, the medial superior temporal area, and then placed monkeys in this apparatus where they could see on a video screen this flow pattern. And as you can see, in A, for example, the thing that you're going towards is this pole off in the distance, and you're moving towards it. So as you might expect, all of the gradient here, this gradient here is flowing past you like this as you move closer to the object. Another view has you coming in at a tangent to the same object, so the flow is coming, kind of like this, right, as you're venturing past that object. And anytime they change the flow patterns, so they would have the same object, right, but different flows heading toward the object, different neurons in the MST area of these monkeys' brains would light up. So some neurons would light up, would activate for this flow pattern here. Different neurons would activate for this flow pattern here. So here we have the parietal lobe. And then we have the medial superior temporal area. Remember, this is the where part of the brain, and this is the what and how, right? So basically, the information for how to navigate through the how, what, and how stream, how to navigate, is located here in this part of the brain. And then, of course, we have the premotor area, which is the mirror area, which we're going to talk about later on. So for these neurons, for example, they would show in this example here, they would show a pattern that, for example, had a bunch of dots moving in a circular fashion. Okay, and this neuron here, neuron A, would not be activated by this circular, by the dot moving in the circular pattern. However, or dots, I should say, moving in a circular pattern. However, this same neuron would respond vigorously, as you can see here by these little action potential spikes here. And this is from 0 to 1, it's from 0 to 1 seconds, right? So this is time in seconds. Whenever the dots look like they were doing an expansion, like coming from the distance and then exploding in your optic array as you walk by, this neuron would fire vigorously. Concurrently, they found another neuron that would only respond to a circular pattern but would not respond to the flow patterns of expansion. So as the monkeys did this task, right, as they were watching and watching the optic array as it was flowing past them, one of the things that they did was they stimulated those neurons that were associated with specific patterns. So, if the monkey, say, for example, was watching the flow pattern heading straight at the pole in the distance, and then they stimulated the neurons that were associated with watching the other flow pattern, the monkey would adjust its behavior to show that it was perceiving the other flow pattern, even when it was watching the straight-on flow pattern, just by stimulating those neurons. Uh, you could change the perception. Which is pretty powerful evidence that this part of the brain probably is involved somehow in helping us to perceive particular flow patterns. So, for example, here's a simple example. So the monkey's watching this particular flow pattern, and it's either moving to the left or moving to the right. Whenever the monkey's allowed to watch the flow pattern without any stimulation, it would say, oh well, it's kind of just 50-50, right? I'm just going straight. But if the flow, but if we stimulated the neurons that were associated with watching a flow pattern move to the left, if we stimulated that while the monkey's looking at the straight flow pattern, you see that the monkey's response patterns for each trial significantly increase. In other words, the monkey is telling us that it perceives that it's moving to the left when in fact it's viewing a straight on flow pattern, but it's the part of the brain that tells it, or the part of the MST that tells it when a flow pattern is going to the left is being stimulated. So car driving is a great example of studying and looking at optic flow, right? So there's a classic set of experiments by Landon Lee where they fitted a car with different instruments to measure how a person was using the car and what they were monitoring in order to navigate the car. So they fitted an instrument to determine how the angle that the wheel was being spun, so whether it was straight on or being angled, right, what direction it was turning, the speed of the vehicle, and they also put in cameras to watch the gaze of the driver so that we could see exactly where the driver's looking in their optic array. When you're driving straight, it turns out, when you're driving straight, you're looking dead ahead, but you're not looking at the focus of expansion, which makes sense because the focus of expansion is where where the optic flow is originating from. But as a driver, you're more concerned with things right in front of you. So while we are looking ahead, we aren't looking at the focus of expansion when we're driving a car. Rather, we're looking directly in front of us. When we are negotiating a curve, we are not looking straight ahead. We're actually looking at at a point. We're actually looking at the curve at a tangent point right on the side of the road to determine how far away we are from the curve. So when they put all these data together, it indicated that we don't just use optic flow when we're driving. We also use the position of the car relative to certain fixed landmarks. And of course, you know this, for example, if you've ever driven on a street or on a highway that does not have, or especially on a highway or an expressway that does not have the lines, the lane lines that determine the lanes. You know, it's really hard to stay in a lane if you don't know where the lane is. And so that's really good evidence that we use a lot of different landmarks and a lot of different components of our environment to navigate a vehicle. So here's a picture here of these findings. So when we're driving, and if we're driving off in the distance, right, here's our focus of expansion, and of course all of the elements of the optic array expand from this focus of expansion. And when we're driving, we're not focused over there. We're focused right here. because we want to see moment by moment what's in front of us as we're driving our car. Similarly, when we're negotiating a curve, we tend to focus on the a spot tangent to the inside of the curve that we're driving, probably to be able to judge our distance and our the location of the car relative to the curve. Walking, just walking from point A to point B, walking through a crowd or walking through a, some sort of crowded area or area that has a lot of things in it, is actually a very complex task if you think about it. One of the things that is interesting about walking is we do tend to point our bodies toward a target. Whenever we are walking towards a target, and if that target moves, we do point our bodies in that direction. Um, so we orient our bodies completely in the direction of the target that we're going. You've noticed this, for example, if you're walking towards somebody and they're at a distance and they start moving, you orient your body and follow your target. It turns out that when people are blinded, if I were to put a blindfold on you, people are actually pretty good at guessing where they're at in an environment. Um, and here's an example here of us navigating through a very simple environment, that is, walking towards this tree, right? If we walk, whoops, sorry about that. If we walk towards the tree, right, and then if we go orient off course to the right, we correct back to the tree, and then we arrive at the tree. We are constantly reorienting ourselves to a particular target. If you've ever, one of the things that you learn in Boy Scouts or in the military is how to orienteer across land. And one of the things they teach you in those courses is, if you know you need to be headed, for example, in a particular direction, like north, south, east, or west, what they tell you to do is to determine what direction you need to go with a compass, and then find an object that's in line with where you need to go that you can see, and then walk towards that object. Once you get to that object, find another object that's in line, next in line, in the direction that you need to go, and follow that object. This is because we want to have a visual cue. We need to have a visual cue. If we don't have a visual cue, if we're not paying attention to a visual cue, we will tend to drift off. So here's an example of an experiment where we had people blindfolded and asked them to take a look at an environment, and then put on a blindfold, right, and then uh, walk a certain way, a certain number of steps, and then turn and face the object that they saw off in the distance before they were blindfolded, right? So we had them spot a target, and then blindfolded them and had them walk, and then told them to stop and turn toward the object, and then told them to turn back and keep walking, and then turn again and face the object. When we ask people to do this, they're really pretty darn good at it, right? So I'm here, and I start here, and I look at the object, which is indicated by this red dash line here. Then I put a blindfold on, and I walk a certain distance, and then I'm asked to stop and then just guess where the object is by turning my body towards it. So I do, and I guess it's about here. Then I'm asked to turn back and go straight, and then again judge where the object is, and I judge about here. And notice that these judgments of where this target is are pretty good, which indicating that when we're blindfolded, and if we know the environment that we're in, if we know like where all the furniture is and where all the objects are, we're pretty good at judging where we are relative to that object. So we can reconstruct the flow in our heads pretty well without visual information. You know this if you've ever had to walk in a completely darkened room in your house. In your house, you know where all the furniture is, you know where all the gotchas are. So, and you can walk pretty well through your house. you can navigate pretty well through your house even when it's completely dark. Now you might stumble every now and then and bump up against a wall every so often, but for the most part we're pretty good at judging how things flow around us even in the absence of visual information.